Okay, so we can consider more general model of information cascades or herding, but let's stop at this moment to think about what are some lessons that we can take away from this herding experiment that we have talked about. So the first lesson is that cascades can be wrong, right? So how do we see that here? So suppose for example, in the thing that we have been discussing so far, that the urn was actually majority red and not majority blue, right? Now, if the urn was majority red, what's the probability that the first student is going to draw a blue marble? Now, that can happen with probability 1 by 3. Why? Because there are three balls and only one of them is blue. So the probability of drawing a blue marble is 1 by 3, right? So similarly, for the second student, if the urn was actually majority red, there is a 1/3 probability that the student is also drawing a blue marble, right? So these are independent draws. So that means that the joint probability of them drawing both blue marbles from a red majority urn is 1 by 9, right? 1 by 3 multiplied by 1 by 3. Now, that means that there is a 1 by 9 chance that even though the urn is majority red, both of the students are drawing a blue marble and are going to say blue. And that will lead to basically everybody saying blue, right? Remember, this is the logic of information cascade, that if you have the first two people saying blue in our experiment, then everybody else is going to ignore what they are going to draw and they are going to say that, right? So you end up with a 1/9 probability that we are going to reach to a wrong conclusion, that everybody is going to be wrong, right? And this probability does not depend on the number of person given the logic of the information cascade, right? So that is a very interesting result. The second important lesson that you have is that cascades can be based on very little information, right? So this is because people start ignoring their private information once a cascade starts, right? So only the pre-cascade information influences the behavior of the population, right? So for example, if a cascade starts relatively quickly in a large population, most of the private information that is collectively available to the population is not going to be used. So in context of the example that we discussed, remember that the cascade can start at the earliest after just two guesses, right? So after that, imagine that you have a class of 100 people. So then the information that is there for the next 98 people are not going to be used by each of the people, because they're all going to kind of like just make their decisions on the basis of what they actually kind of like heard the first two people guess, right? If they guess both the same thing, right? So you can have hypothetically a situation where you had the first two draws being blue, right? And then each of the 98 people, one after another, drew red, but all of them are going to ignore their information and just stay blue based on the information that was there, right? Okay. The third lesson that you have is that the cascades are fragile, right? So we already saw in the previous point that cascades can be based on relatively little information, and that is what makes them easy to start. But it also is a weakness in the sense that relatively little information is also what makes them easy to stop, right? So why does that work? So let's take again the example of this herding experiment that we have been discussing. Imagine that the class had 80 students. The first two guesses were blue. And so you had the logic of the informational cascade working out that all of the guesses are going to be kind of blue, right? Now, imagine that suddenly students 40 and 41 drew red marbles, and by mistake, kind of like, they kind of revealed that these were the red colored marbles to the class, right? Now, in this case, the information cascade has been broken, right? Why? Because now the students not only are hearing what students 40 and 41 actually are guessing, but they're also seeing what they actually drew, right? So now, think about it, when student 42 comes, he has actually got four pieces of information: that the first student drew blue, the second student drew blue, but the student 40 and student 41 drew red, right? The middle ones can all be ignored because that was the information cascade effect going on. So there was very little information, right? So when student 42 is going to make a guess, is going to have this idea that you have got that two draws of blue, two draws of red. And so basically you should be making a decision on the basis of whatever draw that you now observe, right? So the information cascade has actually kind of like is going to be kind of collapsing here, right? So why is this working? Because everybody knew that the initial run of 39 blue guesses had very little information supporting it, right? In fact, the only information that was there was that the first two were blue guesses, right? Blue balls. The other ones were just informational cascade, right? So it became easy for new information to come in and to overturn the previous information, right? So that is what makes information cascades fragile. So what that means is that even if they have persisted for a long time, they can be overturned with comparatively little effort. But the main lesson to be drawn from this example so far that we have been considering this week is that you have to be careful when drawing conclusions about the best course of action from the behavior of a crowd or a group, right? So crowd can be wrong even if everybody is rational, optimal, right? And everybody is taking the same action. That is one lesson that you should take away from this example, right? So this is a very interesting contrast with this wisdom of crowd reasoning, right? So this is a very famous catchphrase, right? What is the wisdom of crowd? So this relates to the idea that the aggregate or the group behavior of many people with limited information can sometimes produce very accurate results, right? So these were kind of like historical experiments that they were there concerning the number of jelly beans in a jar, where you have a group of people in a fair, let us say, who has to go and guess what is the number of jelly beans in a contained in a jar. So it was often found that while if you are considering individual opinions, some of them are accurate, some of them are kind of like very far off from correctly guessing the number of jars. If you look at the average, often the average was not very far away, right? And there's also a very famous historical experiment where people tried to guess the weight of a bull at a fair or a mela, and there too kind of like there the average guess was actually much better than if you consider individual guesses, right? So this is coming in from the implicit assumption that people are guessing independently, right? So each of the people have private information and they guess independently without knowing what the others have guessed. However, we see that this logic breaks down in the case of information cascades because there the guesses are no longer independent, right? Because if they're guessing sequentially or in order, it and they can observe the earlier guesses of the others, then basically they are taking information on the basis of their private information as well as from what they infer about the private information of the others, right? And in this case, there is no reason for this wisdom of crowd reasoning to kind of like hold true, right? So let's talk about a couple of applications of this idea of cascade. So the first one is to group decision making situation in which you can imagine that there is a committee of people who are sitting around a table and discussing potential solutions to a problem, right? Particularly, they're deciding whether they should hire candidate A or candidate B for a particular job, right? So in this kind of situations, often the common way in which these discussions are structured is that you go around the table and each of them are going to say that whether they think candidate one is better or candidate two is better, right? However, if you have this sequential kind of like discussion happening, and if you assume that all of the participants think that they have roughly equal insight into kind of thinking what is the best worker, then you have all the ingredients for a cascade to develop, right? So for example, if a few people initially favor A, then others may kind of also lead to the conclusion that they should favor A, even if their private information would suggest that, B might be better, right? Why? Because exactly of the reason of the cascade, right? So this is not just you are trying to conform to what others are saying. This is a more kind of a rational explanation where you think that, the other people also have information, you also have information. So when you are deciding who to kind of like, if you like, opt for A or B, you are taking into account what the others are saying. That also reflects some information that they have, and you're combining that with your information, and then you are doing it, right? So that is one issue that actually kind of like happens, right? So what are some solutions here? So the idea is that perhaps, before kind of like, coming to a decision, you should actually kind of force people to come to a partial decision on their own independently before entering that discussion phase. So that is one useful thing that you can do. The other useful strategy that can lessen the chance of a cascade happening is that you kind of allow the people who have more information compared to the others. If you know beforehand, some people have more information than others, you allow them to kind of like speak first, right? And then kind of like that actually reduces the probability of you reaching a wrong end here. So another application is in the concept of marketing, right? So marketers also use the idea of cascades to attempt to get a buying cascade started for the product, right? How does that happen? So basically, the idea is that if you can induce or convince an initial set of people to adopt the product, then those who make purchasing decisions later on would also adopt the product, even if the product is perhaps not better than any other competitors. Why would they do it? It's the same logic of the cascades, right? So if you see first a set of people adopting, then you think that perhaps these people have more information about the quality of the good, and then you ignore your information whether you think this is superior or not, and then you decide to go ahead and purchase the good, right? So this is, of course, more effective. If you think about the cascade story, this is more effective if people are only able to observe whether a product is adapted or not, and not whether kind of you have what the customer satisfaction is, right? Because if you are observing how satisfied the customers are with the product, then it's as if you are kind of like getting to see the color of the ball as well as seeing what they're guessing, right? So that is the analogy, if you like. So if payoffs from earlier customers are available, so if you have got customer ratings that are also available in addition to seeing whether how many people purchased or not, this can actually help to prevent a cascade of bad choices coming up. So the discussion that we have had so far is based on this chapter 16 of the textbook mentioned in the in your course website, which is this networks, crowds, and markets. And this chapter is also available to view for free online. It also contains a more general mathematical description of information cascades models. But I believe that we have been able to get the majority of the insights that we had from considering this stylized example and also looking at the various lessons that we learned from